Alright, so hopefully what we're going to do very briefly in this video is to go through our 6061 T6 aluminum data, compute our engineering stress strain curve, correct it, and then convert it to a true stress strain curve. Now I have my data set. I'm going to use Excel, and just going to load that data file in here. Here's that text file I talked about. I'm going to open it, and here's the import wizard in case you haven't done this before. We're going to do a delimited. Let's see what we do when we hit next. Looks like it's got everything in the right columns, and then I'm going to hit finish, and now I have my data in Excel. They have some of this data here is here's the extension, time, load, and strain. I don't really need this first column. It's the same thing as over here, so I'm going to delete it. There's the time. We'll keep that. We're not going to use it, but we'll keep it. And I'm going to get, let me just go ahead and get rid of this data here. Maybe we should keep it. We'll get rid of some of that. Okay. So this started out with a 1/4 inch diameter. I'm going to put that in here. We're using our English standard units. That's okay. You may be more used to metric units if you're an international visitor here, but that's fine. It works just the same way. So what we have is a load and the strain, and so what I want to first do is I want to compute my engineering stress. Okay, now the way we plot our stress strain curve is that the strain's along the x-axis. So I'm going to leave a little space. I'm going to put here a stress, and I'm going to have units of this as pounds per square inch. So I'm going to take my first cell for my load, and I'm going to divide it by pi over 4. And then I'm going to multiply it by my diameter squared. And I don't want that to change, so I'm going to put the $sign here in front of this. So I copy and paste it. Okay, so that's my first stress level. Now, that's almost, that's more than 5.5 KSI worth of stress. That's a pretty good stress. So we cannot ignore the strain. So now I have my first strain value. And the L naught was 1 inch. Now, because my gauge length is 1 inch, my engineering strain, and I can make sure that this is labeled as engineering stress and strain. It's just going to be that same value. Now, I'm not going to bother dividing that through. So I'm just going to do this. Windows 2010 doesn't have this handy feature, but this little drag box you can drag down there. We're going to get to the end of our data. I'm going to copy this. I come down here. And paste it. So now we have all these values in here. Let's take a look at both of these versus data point number, or time, if you will. Let's insert a scatter. Now let's highlight a column first. I guess a line plot should work. Let's do that. Okay. Let's get this way up here. So this is the stress versus data point number, or you can think of it as stress versus time. Looks like right around here is probably where I removed the extensometer. Now here's that point where I talked about in the video where this does not meet up with zero stress and strain. Okay. Let's do the same thing with strain and let's see what this looks like. Strain versus data point number. Let me get this back up at the top. And yeah, right around here is where things kind of went crazy with the strain values. So I must have taken the extensometer off somewhere around this point. See where this is kind of flat? That's probably where I had the testing machine paused. So it was paused in time, and at this point I took it off. Alright, now let's plot our stress versus strain. Oops. We'll insert a scatter plot. And I did it the wrong way. Let me fix this. So really this should be K and the other one should be J. Okay. Alright, so there's the first crack at our plot. Now if you notice, like I said, this has some weird stuff going on at this point. This is after the extensometer removal point. So we need to locate that point and we need to suppress the graph in that region. So we're looking at probably somewhere around 489. So if we go down in here, we had a couple of blank lines. So if we plot everything down to maybe, we'll take a look, 489 looks about in this area. Okay, and really the data doesn't start going a little bit crazy until maybe about this point here. See how it starts to drop. You may even see some negative numbers. Now the stress still continues to rise, like I said, but it looks like we're good up until maybe data point 509. So let's go in here and let's edit the data and just go, what did I say, 589. Okay, looks like we still have some of it here. Let's check and see if I did what I thought we did. You'll probably see me make some mistakes in this. You know, that kind of thing happens. See if we can find a better spot where this data starts to get a little bit crazy. Okay, so I wasn't quite at the right spot. I think it was 489 or something like that. Okay, so it looks like it's pretty good here until maybe 510, 509. Good. Maybe I just looked at that wrong or typed it in wrong. So let's change this to 509. And there we have a pretty good looking curve at this point. Now there's some things that you should probably do to this to make it look more professional. Put your labels on your axes and everything. We'll get to that eventually, I think. If not, I'll refer you to my other video where I go into great detail about how to use Excel to find all this. Well, the next thing we need to do is we need to figure out what the slope of this line is. Let me do a little bit of change up on this. Let's make these a little bit smaller. Okay, so I'm not going to do a connect the point in it, and you know, I guess that's fine. Looks like that where I took the extensometer off, there's still a little bit of residual from that, but I think that's okay. So I'm going to copy this plot, and I'm going to add another line up to where it looks like it stops being linear. Or maybe I'll just edit this one. So this is about 43.5 KSI. So that would correspond to maybe around this point 156. Let's see what that looks like. So now I'm going to change this data range and edit this to be 156. Still have a little bit of curvy in there. It probably wouldn't hurt if I took it down to maybe 35 KSI. So let's do that. There should be enough data points to get a linear regression line off of that. So maybe 123. Some of these materials, they just keep looking a little curvy. You kind of have to go with it. Now we do have an advantage that we know what the modulus of elasticity of aluminum ought to be. And I think we'll end up getting pretty close to it. Alright, so now we have that data. We're going to select it. We're going to add a trend line. We're going to do a linear, and we're going to display the equation and the r squared on this chart. We need to format this, and let's use maybe 4 decimal places. Maybe we want to use scientific. Okay. And so that first number is our modulus of elasticity. Don't worry about the intercept for right now. We have an r squared of 0.999. That's great. That's really very much a straight line. But now if we look at this number, let's put it down here, 1.0181 E7. If we wanted to express that in engineering notation, that would be 10.2 times 10 to the 6. So this would be PSI. 10.2, let's do it this way, times 10 to the 6. Or we would say 10.2 times 10 to the 3 KSI. Now that should be really close to what we would expect for the modulus of elasticity of 6061 T6 aluminum. Let me do a quick web search and see what I could find. Okay, so I did a quick Google search. This is ASM datasheet, modulus of elasticity. They got right at 10 times 10 to the 3 KSI. And we got 10.2. So that's really pretty close. Now, why would that be a little bit different? Well, it could be maybe our extensometer wasn't completely calibrated in that range. It could be just a different batch of material. But we're going to go with this 10.2 number, and that is really a pretty good number. Okay, now what we need to do next is we need to basically extend this line until it hits this axis so we can find our adjusted strain. Let me pause again, and I'll set up the math to show you what we need to do to figure that out. So right now what we have is we have sigma is equal to E epsilon plus B. We'll eventually want to correct this so that we shift it away and get the strain, not the B value, but the corresponding strain value for the intercept. Okay, so we want to find this point right here. What we want to find then is we want to find the location along the epsilon axis where sigma is 0. Basically, we want the x-intercept, I guess. So here we have sigma is equal to our modulus times epsilon plus b. And the regression line equation actually gave us both E and the intercept. Now, if we want to set sigma is equal to 0, then we're going to have negative b is equal to E times epsilon. So the epsilon should be equal to minus b divided by E. Well, let's see what we had for our y-intercept from our chart. So I'm going to write this number down. 5.862 times 10 to the 3. .862 times 10 to the 3. Then we're going to divide by our modulus of elasticity. Oops, what we said was 10.2 times 10 to the 6. I can do this on the spreadsheet, but let me just go ahead and grab my calculator here. It's going to be a small number. .862 times 10 to the 3. We're going to divide by 10.2 times 10 to the 6. And what I have is minus 574.7 times 10 to the minus 6. So what we're going to do is we're going to add the magnitude, or we're going to subtract this number from every single value in our stress strain curve. Alright, so let's see, let's go back to our spreadsheet and let's have another term over here. That's our offset for our strain. And let's see, I said that should be negative 574.7 times 10 to the minus 6. So we have about 575 microstrain of an offset. Okay, so now what I'm going to do is I'm going to copy these two over here. There's my adjusted strain I'm going to have. I'm just going to take the same stress value and I'm going to take the strain and I'm going to subtract that value, and I'm going to put these dollar signs in it so it doesn't change as I copy it down to the end of my data set. Let's find the end of this data. Now I know that I don't go all the way down here, but we'll worry about that in a moment. Let's see. Take our stress strain curve, we're going to copy this one, paste it over here, and instead of using J and K, we're going to use U and V. So let's edit this data. Let's see, that's the strain, so that's what I'm going to use V now. And I'm going to use U over here. Now if I've done this right, and there's always a chance I've made a mistake, if I've done this right, this should show a plot that goes through the origin. Okay, so you see there's a tiny shift from what I had over here. If I were to change this range, okay, you see it doesn't start at 0, 0 anymore. Alright, so now I've shifted it, and now I'm in a position to convert my engineering stress strain into my true stress strain. Now for this I need to be able to take a look and find out what my ultimate stress is. Looking at this, and well, let's see, there's a couple things we can do. Let's do a maximum function. Oop, went the wrong way with it. Okay, so the maximum looks like it's just a bit under 50 KSI. So that would take us until maybe it looks like this point right here, line 267. So now I'm going to take this, I'm going to paste it one more time, and we're going to go down to, like I said, 257. And you know, maybe it's I didn't quite get it, but it's pretty close. 49.48. Let's see what that point says. It says 48.37. Let's add a few more data points. Let's see if we can find it exactly. Let's drag this down so I can see what that number is. 49.481. Okay, right here. 409. Data point 409. Okay. Now we have a little more data to work with. Now what I'm going to do is let me just copy this data up until column 409. We got an extra one in here. There we go. Now, as we discussed, this is the end of the range of applicability of our conversion from engineering to true. And let me find those formulas. All right, here it is. I need to take 1 plus the engineering strain, and I need to multiply it by the engineering stress to get the true stress. The ln of 1 plus the engineering strain gives me my true strain. So let's see if I can do that. So let's type over here true stress and true strain. It thinks it's a Boolean operator, but that's okay. We're going to have the same units. And for this conversion, we'll take this number and multiply it by 1 plus this number. Okay, and for this one, It's a function. I think that's right, but we'll find out in a second. The ln of 1 plus the engineering strain and what I'm going to do is I'm going to copy it and paste it throughout my column. And now let's do this. Let's take this one, paste it over here. I want to keep this in here, so what I'm going to do is I'm going to add another data set, which will have these x values. Oops. It's going to complain a little bit. Excel is a little funny this way. So I want to use A, K, and AL. So we're going to edit this. I'm going to copy this, cancel out of that. Now I'm going to add a series. And for this, this is my strains. This is the AL. For this is going to be my AK. Alright. Let's shrink this down a little bit. And now finally, we have a comparison between our engineering stress strain curve in blue and our true stress strain curve in red. Let's see if I can make this a little bit bigger. One of the things that you'll notice is that there's really no deviation to speak of in the elastic range. You start to have a little bit of deviation as soon as you start to have some yielding. It becomes more significant as you approach the ultimate stress. So here we have the difference between 52.7 KSI true and 49.48 engineering stress. But also this point maps over here just a little bit. It's a little bit less true strain than it is engineering strain. 0.63 versus 0.65. Good. Now for your homework, if you're one of my students, please make this graph look a little nicer. Add your axes, add your labels, and so forth. But that's the point I wanted to make with this video, was the way that we can calculate our true stress and strain curve from our engineering stress strain curve.